Hello, I'm Sotirios Archondoulis, Associate Professor in the Department of Agronomy. And in my presentation, I'm gonna review the 2020 cropping year, and I will try to explain the reasons for high and for low yields. And we will look soil moisture management conditions in the year 2020, and we will try to explain what happened. I'm doing this presentation the last 5 years now, reviewing what happened the last year, and have to admit that this year was quite challenging to interpret some of the experimental data because of the complex interactions that we observed this year. We will talk more through the slides. Let's get started here with the outline. I will start my presentation with the big picture. We are gonna see USDA NAS yield data. We will discuss the weather conditions and some soil moisture maps. And then we will move to field experimental data. I will show you data from soybeans and corn and some example experiments with nitrogen and plant population. I will talk a bit about mineralization and optimum nitrogen this year, and I will talk more about the water issue this year. And in my presentation, I will try to synthesize everything from a systems perspective. And I have here a drawing to show you the system, the plant, the soil, the roots, and the external inputs, among which weather is the most variable. USDA NAS data. We will start with the corn yields, and you see here 5 different lines. One represents a different state. I put Iowa with black and bold, and what you see in this graph is that this year the yield dropped to 184. It was a significant drop from last year, but it was not a big surprise given the conditions we had to deal this year. I mean the ratio and other challenges, weather challenges. The other states did better than the previous year, 2019, and in particular, you see here in the yellow line is Minnesota, where the yield was pretty high. They scored 202 bushels according to the USDA data. In terms of production, Iowa still holds the #1 position with total production a little bit below 2,500 million bushels. Second is Illinois, and then everything else, all the other states. Moving to soybean, again, data for 5 states over 5-6 years. The black line is Iowa. The yield, state level soybean yield, is a little bit below 55 bushels, a little bit below last year, less effect of the ratio on soybean yields. And the other states, Nebraska, Illinois, and Indiana, scored about the same yield, and that's close to 58 bushels. In terms of production, Iowa is the second state after Illinois. And now let's move to the weather and see why we have these yield drops in corn and a little bit in soybean. I will not talk a lot about the ratio in my presentation. I will mostly focus on biophysical factors and weather conditions. And what you see in this first slide is the weather for different crop reporting districts from northwest all the way to southeast. Let me explain one graph. Is the similar style for all of them. Precipitation is in the y-axis for every different month. The orange line is the 37-year average, and the blue line is the year 2020. And according to the data, we had the drought in the middle of the summer, and it became stronger in August, and in September it continued that way. In Northwest, North Central, a little bit different pattern. Northeast different. Central West was probably the worst region in terms of precipitation amount. The Central Iowa, where we're going to focus more, Central East, and the other three regions, crop reporting districts. Quite variable precipitation across the entire state. Noticeable is the big drought in August. As I was making these graphs, one important thing that came to my attention was the variability from one region to another. And then what I did was to look at the previous years, the precipitation patterns. And I focus in Central Iowa. Again, this is the Central Iowa in 2020. And I use here different graphs for different years. And what it struck me is that it was very, very hard to find a year with a similar precipitation pattern. Every year is very different. And that's something we have to deal with. But yeah, that was something that it was kind of interesting, and I wanted to share with you. Next is which is the best and which is the worst precipitation pattern for Iowa. I will focus again on Central Iowa. And in my opinion, this is the best precipitation pattern that we can have in Iowa. Orange line is the 37-year mean, and the blue line is the precipitation in year 2016. What it makes the best, in my opinion, is that we are below normal early in the season until silking. And once we get into silking for corn, precipitation is above normal. Second interesting thing is that the blue line, it doesn't go below the standard deviations here, are within the limits, and here doesn't exist. So this is something very important. We don't want to go over here, because in that case, we will end up to having a very wet year, like 93 or 2010, and you see the corresponding yield drops compared to the baseline, to the trend line. And early in the season, we don't want to be very dry, like the year 98 or 2012. And you see again the yield deviation from the trend line. Another year, which to me is the worst in terms of production and environmental performance, is the precipitation pattern of 2013. Very wet early in the season and very dry during grain filling period. That's the worst case scenario in my opinion. If you want to see more graphs like this or explore different regions, you can visit this website. It's a new tool that we developed this summer. You can easily pick one crop reporting district. I use Central Iowa in my previous slides, but you can pick any out of nearly 100 crop reporting districts. Then you can select a weather indicator. We offer 12 different weather indicators. You can select a year to benchmark, the benchmarking period, and then you can see the graphs. The second weather variable that I want to discuss is the sunlight, the radiation. In 2020, we had a record radiation, especially during summertime. And to convert the radiation to sunny days, the definition we use is the amount of radiation per day is above 20 megajoules per square meter. And as you can see in this plot, in August, we had nearly 27, 25 out of the 30 days. It was sunny. We had no clouds. It was unbelievable sunny, the month of August. And this is why it makes the year 2020 a record year in terms of radiation. I always say that high radiation levels is a good thing, because of the strong relation with the biomass production and the yield. Usually, in our example 2020, we have 17% more sunlight. This corresponds approximately to 17% more yield if all other factors are not limiting. And in year 2020, we had limitations in terms of precipitation and soil moisture. Let me show you some soil moisture maps. Again, you can find this type of information in the website, the crops extension website. And what I present you here is the soil moisture on August 18 for the topsoil and for the subsoil. The yellow the color, the drier the soil. The darker the color, the more moisture is in the profile. And basically, the entire Iowa, except some spots, was totally dry in the third week of August, second or third week of August. But we had moisture in the subsoil, especially in the east part and the south part. But this portion here in the west was totally dry. The topsoil moisture is very important, not only for crop growth, but also for soil nitrogen mineralization. The majority of the soil carbon is in the top 30 centimeters. When it comes to the subsoil, the majority of the moisture here, it goes to supply the roots with water. We don't have so much nitrogen down there as we have at the top. One last issue about the regional scale big picture is the planting time. It was quite early this year, similar to 2012 and 2016. I was joking back there that when we had so early planting time, everyone was saying it's gonna be a year like 2016. And I was agreeing with that and saying, I hope so, and looks like, but you know, there is one more possibility. The year 2012, we had the same planting time. Anyway, let's move forward and let's review now some field experimental data. Here you see a map with experimental locations we had in year 2020. We had a good representation across the state. We had both corn and soybean experiments. Treatments were nitrogen rate, cultivars, plant population, and different biological treatments. We collected enough data using soil moisture sensors and sensors to track the water table, plant growth, yield, protein, and of course, environmental data that I'm not gonna include in my presentation. We had some failures because of the ratio, and this is one example picture, one field experiment that was partially destroyed. I don't include this data in my slides in the experimental results that I'm gonna share with you. One comment I want to make about the ratio and effects of previous management on the impact of the ratio. What we noticed in our experimental fields, it was the plant size. The heavier the plant, the easier was to get down by the ratio. That was the #1 factor in our case. Tillage, fertility, we didn't notice any pattern there. It was the plant size. And of course, the growth stage that was in. Across all the trials with the soybean from northwest, southwest, the average yield was about 65 bushels per acre, and there was variability from one location and treatment to another. Corn yield, on average, we got 193 bushels. Of course, we had ups and downs, and I will give you some examples. Example #1 is the experiment that Mike Castellano and I are working with Bayer Crop Science, where we study combinations of management practices and different hybrids on production and environmental performance. This is an aerial view of the experimental location. You can see here the size of its plot. It's a nice experiment, and what made me happy this year was to see that we compare, I forgot to mention that old management and hybrids, current hybrids and management and future, was to see that the future where we are heading, combo of practices and genetics scored very high this year despite all these challenges with the ratio. This is a central Iowa field and also the drought. Another experiment with Mark Licht, we compared high versus low input management. This is a picture of the experiment. In the high input, we consider 38K plants, 220 pounds nitrogen. The low was 28K plants and 120 pounds nitrogen. And with the high input system, we got close to 10 bushels benefit. I was a bit surprised with this result because I was concerned with the high plant density here and the drought, but I was wrong. And I used a little bit modeling to explain why the high input yield better this year. You see here the blue line is the high, the red is the low input. We got about 10 bushels difference. What is important to notice here, this is the grain accumulation, and you see how the higher number of plants and higher nitrogen rate really affected the initial slope of the grain accumulation. That was the benefit of the high input. And of course, this yielded higher yield. And look at this one. The difference in yield is 10 bushels, but the difference in the total plant N uptake was pretty high. Another experiment, complex one, we studied the combination of 5 hybrids, 5 plant population, and 5 nitrogen rates. We wanted to explore the interaction on the economic optimum nitrogen rate and the yield. Kyle King, a master student, collaboration with Jody Edwards, was in charge of this experiment. You can see the picture of the experiment here. And let me show you some of results for one hybrid. Plant population in the x-axis. And what I plot here, the blue line is the yield, higher plant density, higher yield, and then drops. That was what we were expecting, the shape. But what was a bit surprising, and still trying to interpret this, was the optimum nitrogen rate, how it changed from across the different plant densities. And it seemed that this year, despite the drought, this seems like the best combination. Plants near 40, 38K plants. And it had the lower economic optimum nitrogen rate. Talking about nitrogen, here are some more data from long-term nitrogen experiments across Iowa. The orange bars represent economic optimum nitrogen rate for corn following corn. There was variation from side to side, but it was close to 200 pounds per acre nitrogen. Corn following soybean is the right panel here, and this year was higher than normal. And in general, that was a little bit surprising to us because it was a dry year, so we were expecting lower optimum nitrogen rate. A second point I want to make here is that in year 2020, we didn't see much difference between corn following corn and corn following soybean. Usually, this is higher and this is lower, but this year we didn't get that. We look at the corn yield under zero nitrogen fertilizer, and in this case, the corn following corn plots yielded about 60 bushels, and the corn following soybean yielded about 100 bushels. This is what we usually expect. So the change in the optimum nitrogen rate was not caused by the first point under zero, it was caused at high N rate. So something happened there. And trying to explain that, still working and reviewing the data, but one possible explanation I want to share with you is the soil nitrogen mineralization. The lack of moisture in the soil is not only affecting crop growth, but also the mineralization of the soil carbon. And in June 16, you see the map here of soil nitrogen mineralization. A color, a value near 1, it means optimum, similar to previous years. But a color, a dark color, especially red, it means considerable less soil nitrogen mineralization compared to a normal year. And we believe this is one reason for the high optimum nitrogen rate, because of the less soil supply. Now, you will tell me, we didn't have any nitrogen losses this year because of the drought. This is absolutely correct. But when we compare mineralization flux with the leaching flux, mineralization is much higher always than the amount that we are losing as leaching and denitrification. I had a little closer look at one field, Central Iowa, the one that I mentioned, high and low input. I used modeling again, and I outputted the daily mineralization. You see here, this is the cumulative mineralization, and basically the curve flattened out in August and September. We got no extra nitrogen during that period because the topsoil was totally dry. I ran a second simulation, and in that simulation, I entered enough water to get to the potential yield. And in this case, you see the extra water, it starts making the difference from here. And you see the mineralization from the soil is not getting flat, but is going up. And the difference between these two lines is 75% more mineralization when we have no water limitations. And of course, the yield goes up by 38%. It goes to 275 bushels. And this is a nice illustration of the yield gap. Nothing we can do about it. We didn't have irrigation to apply in this experiment. I explored a few more options to see what we could have done differently in 2020 and have higher yields. The baseline was 200. I showed you previously the full irrigation scenario. And here I present a 2-inch irrigation scenario and 1-inch irrigation scenario. So if we had 1 inch of water, extra water in 2020 in August, we will getting 15 bushels more. In this example, the planting day was end of April. If the planting was 2 weeks earlier, we will getting another 10 to 15 bushels benefit. It was a no-till in the baseline scenario. If we had tillage, it will be less yield in 2020. Tile drainage, a little bit yield drop 1-2 bushels. And in the scenario of fewer plants, we didn't get higher yield. We got lower yield. That was a little of surprise to me. It was 5K lower plants. The timing of nitrogen application had no effect. We couldn't change the baseline yield. So this is how we could go up the yield with some management practices, some that may work and some may not work. But I want to draw your attention on another issue, which is the subsoil moisture and the water table. The blue line again is the 200 bushel that we observed in the experiment and we model as well. And this is the irrigated. I want to bring into the discussion the red line, which is the yield that we would have if the soil had no shallow water table. So in this case, the yield will be nearly 100. In other words, the yield credit from the water table, it was 100 bushels. I know it sounds a lot, but I think this is what happened in 2020. The shallow water table that exists in central Iowa soils really helped to buffer the lack of water. Let me show you one picture. This is from an experiment that I'm working with Stephen Hall, Mike Castellano, Matt Helmers, and other colleagues from Iowa State University. And there were some structures to isolate the soils. Basically, this block here has no water table. And you see the picture September 12th, the plants were totally dry. And next to it are plants without the structures that get the contribution of the water table. So I think this picture is pretty convenient, and the yield data that we got from here to justify the simulated credit of 100 bushel. And this is a view of the year from the plots without the water table. Now, I want to clarify and make sure that everyone knows the term water table is the soil layer that is fully saturated with water. And this is the reason why we put tiles. So this is the simplest definition that I can offer for the water table. Let me show you some results of the water table dynamics. In 2020, we had water table wells and sensors to record the fluctuation of the water table in all the locations in Iowa, most of them. And in this graph, you can see some results from west to east of Iowa. This is the depth of the water table. 0 is the surface from the day that we installed the well until the day that we took it out or there was no water over there. In the Carroll County, west part of Iowa, these soils there, they don't have shallow water table, but they have a high water holding capacity. And this was reflected by our measurements. In the east portion, Marshall County, it was high, it was shallow, the water table, near 2 feet, and then declined linearly over time. In central Iowa, Boone and Story County, the water table was somewhere in between these two extreme situations. Now, let me draw your attention to within a single field. We get variation in the water table from one region to another, but we get variability in the water table even within a field. And in one field with tile drainage in central Iowa, we had 10 to 12 wells. And here you can see the range of variation that exists even within a field. In another experiment, a couple of miles away from this one, we had 4 or 5 wells and in a field without tile drainage, and we had over there also variability. I compared the field with tile drainage and the field without tile drainage to see if tiles affected the fluctuation of the water table. And according to the data, besides early in the season in June, it was pretty consistent. There was no effect of tile on the water table depth. Usually the effect of tile comes here when it's pretty wet. The next interesting comparison that I did was to compare the water table trends from the year 2020, is the previous data that I showed you in the previous slide, orange line, and I added the year 2019, the blue line. You remember last year it was wet and then became very dry, and then it was wet again. But what was interesting to note here is that the Iowa soils, it takes months to get empty. Look here, to go from that point to that point, it took nearly 100 days and 13 inches of rain. But to fill up the profile, it took 34 days and 7 inches of rain. So it gets long time to get empty, but a couple of weeks to get full. Second data set to justify this is data from Kanawha this time, water table fluctuations, 2011, 12, 13, and 14. It was around 3 feet in 2011, and then we had the big drought, and nearly the end of summer of 2012, it was 14 feet. It took 400 days. And then from that point to that point, 50 days to get full. So the difference is pretty obvious here. The last example to justify my statements that takes months to get empty but weeks to fill up. Data from US Drought Monitor. You see here the bars where the darker the color and the higher the darker the color and the more that is filled, the higher the drought. Year 2012, 2013, big magnitude of drought, but you see it became no drought within a couple of weeks, days there, and then we started again. This is the situation that we are today. This is percent of area in Iowa that has some drought. We don't have much in the red category, and I personally believe we have plenty of time for the soil profile to get refilled. Now, I want to take the rest of the time and talk a little bit more about what is going on with the water in the soil profile and the interactions with the roots, and how much of the subsoil moisture is available to the plant roots. I will start with this conceptual framework from a publication in 2017. And the simple answer, actually there is no simple answer how much is the contribution. It's very complex. And different soils have different capacities to store water and get benefit from the water table. Let's start and say a few more things about that. This is the sandy soils, and the dashed green line is the penetration, infiltration of the water inside the profile. And if the soil has a water table, it can have a huge upward flux, but it cannot go very high. This is because of texture and all the physics that involve there. On the other side, where we have a clay soil, usually we have higher moisture content. The water from the rain doesn't go very deep, is accumulated in the top profile. And when there is a shallow water table there, the capillary fringe can go very high, but the amount of water that can go up is not that much. So there are all sorts of complexities involved in the equation how much of the water can be used for water uptake by the roots. A simple way to give you an equation to calculate, which is very difficult, the water available to plants, this is what we do in modeling, is this one. The water available to plants equals the soil water, which we know can change every day, minus the wilting point. The wilting point is this line here, times the rooting depth. Let's assume that the plant has no constraints, can go easily to 5 feet, times the distribution of the roots. Roots down here, they don't have the same capacity as the roots up here to take up water. And then we have the plant genetics factor, which is the ability of the roots to take up water. So it's complicated, the story. And if I try to illustrate this here, the water available for root uptake is this portion here of the profile. I forgot to mention that the black line here is the fill capacity and the dashed line here is the saturation. The distance between wilting point and fill capacity is the soil water holding capacity, and we should be careful to not confuse this one with the water available for root uptake. One last factor that I want to get in to show you how difficult is the calculation is that in a majority of soils we have shallow water table. And this, yes, it affects the subsoil moisture, but through capillary fringe, it can affect also the topsoil moisture. And I have one example to illustrate that. I will go back to the experiment with the high and low input, the FACS experiment. I showed you that before, yield with water table, yield without water table. What is new in this slide is the water table fluctuation in this field is the blue line, and the green points are the real measurements to convince myself and also to illustrate to you that the model can capture this variability. So the next thing was to compare the moisture of this type of crop with water table and without. And in this graph on the left, you see the whole profile moisture. And I convert the units to a relative scale. That means 1 is full of water, the soil profile, 0 is at wilting point, there is no water. And you can see here the contribution of the water table. So all this distance, this is the benefit that we get from the water table. And in this particular year, in both cases, the profile got empty of water, but the difference was here, the timing. The soil without the shallow water table, it became totally dry 30 days before the other one. And this probably explains why in this picture on September 2nd, that was totally dry, while the other one was not. So you see now what is going on with the soil moisture in a field with and a field without water table. The next thing that I did was to see how much was the water. And by difference in the total water uptake with and without, I estimated how much was the contribution in year 2020. It was 4.9 inches, or if you prefer, 30% of the total water uptake came from the water table and 70% from the rain and soil moisture. The contribution in the top layer, the contribution was equally in all layers. It was not only in the bottom layers. Plus 1.7 inches in the first layer, plus 1.5 in the second, plus 2.1 in the third, and plus 1.7 from 3 to 5 feet. So that was the contribution of the water table. And in addition to the water uptake, the water table had the contribution also to the soil water evaporation. One important thing to keep in mind is that the water uptake does not always follow the distribution of the root mass, that according to experimental data declines exponentially regardless the crop. And the topsoil layer is the layer that where we really want to have water, because here we have the high soil organic matter. Down here we don't have much soil organic carbon. So it's preferable to get water from the top rather than from the bottom. But that's something that we need to explore more and come up with more data. But in general, what I want to say is that most of Iowa benefits from the water table. Some locations, they benefit more than others, and the issue of the contribution, how much is the benefit, which in some cases can be penalty if you have too much water, rainwater, it's complicated. But if you look at this map here, which is Surgo water table values, the darker the color, the shallower the water table. And if you look the second map here, which is an estimate of the effective root zone, the depth to the root zone where the plant can take up water and nutrients, Iowa is well positioned and get lots of benefits from the subsoil moisture. Lots of blue here and lots of blue color here, besides the northeast part where there are some soil constraints. Blue color in this map shows that the root can go down to 5 feet. So there is a clear connection for most of the soils to get the benefit. And let me show you in the next slide how much this benefit can be. This is one example, and of course the penalty or the credit depends on the amount of precipitation. And by running a simulation with and without water table and calculating the difference in the y-axis, this is how the data looks like. Once we get above 15 inches of rain, we get the penalty. This is the tile drainage need. And when we have a relative dry year, we get the benefit. But the benefit, it depends on the distribution of the precipitation. When you have the drought, it can be from 0, can be 80 bushels. It varies a lot. And this is one soil. If I put 8 soils together times 20 years, it becomes a complex relation, but the pattern is pretty obvious. And as a general rule of thumb, what it seems to me from data analysis is that the threshold to determine the credit or penalty is usually when we exceed or we are below the long-term average precipitation. But that's something that we are working for. Last slide. The conclusions from this 2020 review. First of all, it was an exceptional year. COVID, the ratio, and drought, but production holds pretty good levels in terms of production. And I want to congratulate the Iowa farmers that under such circumstances, they managed to get high production levels. We had record radiation levels in year 2020, but unfortunately, we didn't get much of the benefit of the extra energy. And the reason was the limitation that we had from the amount of water. The distribution of the rain in year 2020, if it was a little different, we would have higher yields. If we had the dry period in June rather than in August, I believe we will have much higher yields in 2020. Iowa soils, one important result was that it takes months to get empty, but weeks to fill up with water. The shallow water tables buffer against the climate variability. And I show you one example, simulation example from the model, where we estimated nearly 30% of the total water uptake was because of the contribution of the water table. And the equivalent, when I convert this to bushels, that was nearly 100 bushels per acre yield for this particular experiment. Regarding the management, we found complex drought times plant population times nitrogen rate interaction on corn yields. something that we are still working to understand the causes and figure out what is going on there. And the early planting this year really helped, really helped. And with that, I want to thank you, my group, for all the work to collect the data. And in particularly, I want to thank Mitch Baum and Caio dos Santos for creating lots of the data that I presented in this presentation, and sponsors that allow us to collect and interpret experimental results. And if you have further questions, I have here at the bottom my email, and I will be happy to follow up and answer your questions. Thank you.